Today our topic is coastal protection. Next, we look at the design of rigid vertical face structure, which is governed primarily by the pressure distribution on the sea side. Here we have a vertical structure where the still water level in front has a water depth of D. Due to wave setup, we have a mean water level which is at delta Z above the still water level and about which the wave fluctuate with an amplitude of A. This produces a triangular distribution of pressure in front of the structure which is maximum at the toe. Recall that the equation for pressure looks like this, whereby the first term is the hydrodynamic pressure and the second term is the hydrostatic pressure. We are going to assume that the wall is located at x equals to 0. In order to get the maximum pressure at the toe, we are going to assume that the phase term, the cosine term here, equals to 1, and at the toe, z plus d is equals to 0, such that cos hyperbolic of k times z plus d is equals to 1. By substituting the values from the previous slide onto the equation, the pressure term right now can be simplified to be given by this, where again this is the hydrostatic pressure and this is the dynamic pressure due to the wave. Here A is the wave amplitude. Take note that the wave amplitude in front of the vertical phase structure cannot be measured directly because the incident wave will be reflected by the vertical phase and the two will superimpose on one another to form a wave pattern with both constructive and destructive superposition. In order to identify the wave amplitude in front of the structure, we can measure the wave envelope. You can refer back to the topic on wave reflection. So essentially, the incident plus the reflected wave height will be equals to this expression in terms of the reflection coefficient, and it's equals to 2 times the wave amplitude. Typically, the reflection coefficient is approximately 0.9, and by rearranging this equation, we can calculate the wave amplitude using the assumed reflection coefficient and if we know the incidence wave height. Take note that if there is no energy loss, then the reflection coefficient equals to 1, such that the reflected wave height is the same as the incidence wave height. As a result of that, the wave amplitude will be equals to the superposition of these two wave height divided by 2, and essentially that means that the wave amplitude equals to the incidence wave height divided by 2. To calculate the wave setup, delta z can be approximated by this expression in front of a vertical phase structure, and so the structure must be designed in such a way to make sure that its crown level must be higher than A plus delta z above the still water line. A is the wave amplitude and delta z is the wave setup. This will make sure that there is no wave overtopping onto the land side of the structure. Let's look at this example. The breakwater for a small marina is constructed of vertical concrete panels supported by piles. The water depth at the structure is 4 meters, and the panels have an opening of 0.5 meters at the bottom to enhance circulation in the marina. The panel extend 1.5 meters above still water level with a total length of 5 meters. For an incident wave height of 1 meter and a period of 4 seconds, determine the maximum wave-induced force and moment on the breakwater per unit length. Assume still water level on the lee side. assume fresh water, which means that we're going to use the density as 1000 kilogram per meter cube. So first and foremost, using the information regarding the wave period, we are able to derive the deep water wavelength and subsequently the wavelength at this location, which is 4 meter deep. Assuming that there is a reflection coefficient of 0.9 on the C side of the structure. For an incident wave height of 1 meter, we expect that the wave amplitude in front of the structure to be 0.95 meter and a wave setup of 0.15 meter. Using all this information, we are now ready to substitute into the equation, taking note that because the vertical breakwater is exposed to the sea on both sides, so the hydrostatic component of the pressure cancels off one another, and we are left with only the pressure term due to the dynamic wave. Calculating using this equation for a water depth of 4 meter, we get a total maximum pressure of this value at the toe level. In our solution in the previous slide, we have assumed that there is a wave setup of delta z above the still water line, and also when the wave crest is acting on the vertical breakwater, the amplitude is 0.95 meters. So the total is 1.1 meter, meaning that the wave crest will be at position somewhere here, which is still lower than the highest point of the breakwater. This means that there will be no wave overtopping in this case. Also, from the previous slide, we have solved that the pressure at z equals -4 at the seabed is just over 5,000 Newton per meter square. However, because there's an opening over here, that means the pressure due to the wave is not acting on the structure. It will pass through. As a result of that, we want to determine the pressure at this lowest point of the vertical panel. We can use the similar triangle concept. So based on that, we are able to find out that the pressure at this level, where z is equals to -3.5 meter, is just over 4,600 Newton per meter square. Recall that the panel actually is supported by pile at regular interval with opening below, and it is continuous in this direction and in this direction, alright, into the plane in this figure. It is important that we derive the pressure on the panel. Although there will also be pressure on the vertical pile here, it will be minimal compared to the large surface area of the panel itself. So which is why we omit the pressure that acts on the opening part here. Now we have obtained this pressure distribution triangle, which is 0 here and which is over 4,600 here. So we extract that triangle over here. If we find the area of the triangle, okay, we are able to get the total force acting on the vertical panel. So F equals to P, the pressure, times H, which is the height from this point to this point, divided by 2. The total force is 10.6 kilonewton per meter length into the plane, meaning per meter length of this vertical panel. In order to find the moment arm B from the seabed, that is given by this 0.5 meter plus 1/3 of the 4.6 meter over here from the base of the pressure distribution triangle. So we get 2.03 meter above seabed. By multiplying F to E, we get the total moment that acts on the vertical panel, which is 21.6 kilonewton meter per meter. Now, it is again important in this case for us to consider the moment arm from the seabed, because the entire breakwater setup is hinged at the seabed instead of at the lowest point of the panel, which is why our moment arm here E must be measured from the seabed rather than from the lowest point of the vertical panel. What if the vertical structure in our previous example is exposed to the sea on one side, and whereas the other side is the land itself? In this case, notice that the hydrostatic pressure is not cancelled out on both sides, so it will have to be taken into consideration. So we quantify the hydrostatic pressure, which is 0 at the still water level and reaches the maximum at the toe. And from this triangular pressure distribution, we are then able to determine the hydrostatic force. The hydrostatic force is acting at a distance of d/3 from the bed. That is the moment arm, which is 1.33 meter here. And from that, we can calculate the moment due to the hydrostatic force by multiplying the hydrostatic force with the moment arm. That gives us about 105 kilonewton meter per meter. Again, because the vertical panel is only exposed to the sea on one side, we are going to look at the total moment due to the wave. Here, the moment on the entire vertical structure will be attributed to the triangle pressure distribution due to the wave, which is 0 at this point and up to a maximum of 5,125 Newton per meter square at the seabed level, whereas the moment arm will be given by this entire triangle height divided by 3, so that is 5.1 divided by 3, and so the total moment due to the wave is 22.2 kilonewton meter per meter. If we sum up the two, the total moment now acting on this vertical structure is about 126.8 kilonewton meter per meter, taking note that in this case the moment due to the hydrostatic force is much larger than the moment due to the dynamic wave. In yet another scenario, what happens if the land side of the vertical phase structure is made up of saturated soil? Let's say if the soil has a saturated unit wave of 20 kilonewton per meter cube. Let us now look at the pressure from the land side acting on the vertical structure. Due to the pressure of the soil, we have 110 kilonewton per meter square at the seabed level. The total force due to this triangular pressure distribution is then quantified to be just over 300 kilonewton per meter, and by taking the moment arm to be 5.5 divided by 3, which is from the top of the vertical structure down to the seabed, total 5.5 meter. The moment arm is 5.5 divided by 3 multiplied by the force. We get the total moment due to the soil acting on the vertical phase structure to be 555 kilonewton meter per meter. So now we have a clockwise moment due to the soil, and we have an anti-clockwise moment due to hydrostatic pressure and wave. And if we check that, the net moment in this case is 427.8 kilonewton per meter, and it is acting clockwise due to the pressure, larger pressure from the soil on the left in this diagram. So the vertical phase structure in this case will have to be designed accordingly to the forces acting on it for these different scenarios that we have just discussed.